Okay, so next example that we will cover in this lecture is polynomial curve fitting. Here the idea is to have, if we have a number of points, okay, that could represent certain value, let's say this could be temperature and this could be, let's say, days. So we know that on this day we had this temperature, on this day we had this temperature, and so on. But for example, let's say that for certain days we did not have temperature. Let's say our sensors was broken and we were not able to measure data on this particular days, for example. So the idea of this machine learning algorithm is to fit a function that would approximate these points. In this example, we selected function sine of 2 pi x, and that's the true function. That's what we want to actually obtain. But in reality, we don't know that this is a sine function. What we know is the observed data, those blue points. Okay, as you can see, besides having not the complete data, but just a few points, these points do not exactly align with the curve, okay, so with the sine function. And the reason why is because the sensor that measures the temperature is imprecise. So we have certain errors here. Nevertheless, our goal is still to reconstruct the original function. Okay, so in machine learning, most of machine learning problems, we are given with a training data, and a training data consists of x and y, where x represents our input or our measurements and y represents labels. So here we don't really have labels. What we have for y is the temperatures. So we know that this x should be mapped to this y. Okay, so our goal to exploit this training set in order to make predictions of the values y hat. So y hat is our approximation of true y. Okay, and we don't know the true y. We only know a few measurements from this true function. Well, there are different models that we could apply to build this mapping from x basically to y. There's many functions we could construct. In this example, we chose to use polynomial function of order m. Okay, in a short notation, we can use the sigma notation. We can write this down as follows. So we have coefficients w sub j times x sub j, and we go over all the terms, all the monomials from 0 to m. Okay, so the question is, how do we know that our model is good? Or how do we know that our model produced good approximation of the training set, and it will do good also in the future for the unseen data? Well, to answer this question, we have to decide on the criteria. What does this mean to be good? Okay, so we want to find the best possible approximation for a given model. So how do we know that what we obtain is the best, or is it good, or is it bad? So we need to quantify this somehow. And in many, if not all, machine learning algorithms, we need to specify, or we need to determine, we need to design an error function that measures the error or how bad we do. One example of error functions is shown here. So this is called sum of square errors. So this is an error. Error for what? For the pair n. Okay, and we have capital N pairs. So remember, by pair I mean xk to yk. Okay, then I have also akk plus 1 to yk plus 1, and so on until we get to the last element, or last pair in our training set, x sub n to y sub n. So here we calculate the value of function f, which is our model. So f of x sub n will give us prediction, okay, that given by our model, and y sub n is the true value. So if you look at this figure, then f, function f, at the value x sub n, let's say this value, is this. Okay, so this is the value of our function. Okay? This is the value of our function x for given parameter, for parameters w. But the true value is t sub n. So it means that this is error sub n. So this is the nth error, right? This one will be error with sub index n minus 1, and so on. So we will have capital N errors. So how do we accumulate these errors? Well, again, we calculated the difference. This will give us an error. But note that sometimes our error could be positive, sometimes negative. In this example, t sub n represents, which here is in this formula, this is y sub n. So y sub n is the true value, and you can see that it's larger than f of x sub n. So this error is going to be positive. On the other hand, here we see that the function has greater value than the true value of y sub n. So here, if you subtract f minus y, you're going to have positive error. So this is going to be positive error, this is going to be negative error. So if we sum up this positive, negative, positive, and so on, we're going to get a value that could be in fact really close to 0, right? And 0 would identify or will be associated with a 0 error. So it means we don't have any error, and our model does a good job. But in fact, you can see that this is not the case. We do have errors, and it's not a perfect case. So how can we make sure that positive and negative errors would still contribute to the final error? Well, one way is to use square. So if it was negative, we square this, it becomes positive. If it was positive, we square it, becomes positive, right? So when we sum up squares of errors, we will get a positive number. Okay? 1 over 2 is just a coefficient, and in later lectures you will see why we have it. It does not play any crucial role. You can neglect this. The most important part here is this: sum of square errors. What is our goal with this function? Well, our goal is to make this function as small as possible, or we want to find such kind of w, the parameters of our model, that the function e is minimum. So this is our goal. So to find this minimum, usually we solve an optimization problem that we will discuss in next lectures, how to do that. Right now, we assume that we have solved this problem, and we have found that the parameters, the weights, the parameters of our model f, for which this error is minimum, is given by w sub star. So this is a special notation. This is a set of special parameters for which this error function attain minimum. Okay, so if our error function, for example, looks like this, then this is the error e, let's say, and these are the parameters w. Then what we want to do, we want to find this point w star. Okay, and the value of error function is this. So this is what we want to do. So let's say we have solved this and we know what w star is. when we know this coefficients of our polynomial function, so in fact what we did right now, we solved the optimization problem, and the result of the solution is these coefficients. So these are the coefficients that we just obtained. Okay, so the next topic that I'd like to discuss is how to choose the order of our polynomial. So if you notice in previous slides here, we define a polynomial, which is our model, and that polynomial depends on the parameter m. So besides having the coefficient, it actually, before we go into finding the coefficients problem, we need to decide what this value m will be. So the higher the m, which is the order of polynomial, the more coefficients we need to solve, or we need to determine. So if m is too large, firstly, it could be computationally intensive and demanding to find m plus 1 coefficients. And also sometimes we don't even need to have a higher number of coefficients. Why we don't need? Because for higher order polynomial, we might have situation that represented in this picture. So note, here the order of polynomial is 9, and overall we have also 9 blue points. So polynomial of order 9 could go precisely through each of these points, through each of these blue points, for each of these measurements. But looking at the true curve, that in fact usually we don't know in practice, okay, it's actually quite far. We have series oscillations here. So it's not the perfect case. On the other hand, if we go to m equal to 0, so our polynomial is just a constant. So going back to the polynomials, of m is 0, then what do we have here? So this is x1, okay, this is x squared, and so on, and x0 is actually 1, so that's why it's not shown here. So we only need to solve for one parameter. So we want to find only one coefficient, and that coefficient represents a constant. So this is what's shown here. It's just a constant. Obviously, this is not a good choice of m, and the error is large. Here, if m increases to 1, it will correspond to the model that is a line. So let me write this down. So f of x is w sub 0 plus w sub 1 times x. So this is the model, and we want to find an offset and the slope. Still, if you look at this picture, it doesn't look like it's a good model. The error will be large, pretty large this time. So still we have pretty large error. So if I project each of this point, or calculate the distance between each of this point to the this model, you can see the errors are pretty large. Okay, what about m equal 3? So m equal 3, the error visually considerably smaller compared to all previous models, m0, m1. So this one is much smaller, and in fact that's the best model that we could use here. If we increase m to 4, 5, and 6, the error will not change much, but at m equal to 9, error will significantly increase. Okay, so here's an important point. It will not increase on the training set, because you can see it goes through all the training points. So the training error is going to be small. It will increase on a testing data. So if we take a point, let's say for example here, let's say this is our testing point, then the error will be huge, right? It's gonna go off the chart. If we have a testing data point here, the error also gonna be large, and so on. So on the testing data, it will be not the best model, obviously. So this is the best model. We discussed more an intuitive way to choose m. So we plot our model, we plot the training data set, and then we observe that the discrepancy is pretty big. How can we make this automatic so we don't have to every time look at pictures visually? Well, one way to do that is to divide our training data set into subsets. So we will have two subsets, in fact. One will be used in training, so this is also called training data set. We discussed about this, okay? And another data set will be test data set or validation data set, okay? So it could be the same set, or you could even divide this subset into two subsets. One is going to be testing and validation data set. Let's assume for now, for simplicity, that we divided the whole training set into two. One is training data set that is used in training. So we optimize our model, or we solve for these coefficients on the data within this training data set, and testing or validation data set is used to solve problem of overfitting. So this was the problem of overfitting, this was the problem of underfitting, and this is the perfect case. Okay, so when we divide it into two subsets, training and, let's say, test data set, we also have to have a good criteria, okay, for deciding whether the training was good or not. Before, in previous slides, we used sum of squares error. Sometimes it's abbreviated as SSE, so sum of squares, sum of square errors. And here we will study a slight modification of this SSE function, which is called RMS and stands for root mean square. So we take SSE, so this is SSE, we multiply it by 2. The reason why we do that is because, remember, we divided by 2, so we multiply it by 2 now. We multiply it back. Next, we divide by n, and n is the number of samples in a training set. The reason why we do that is because our training set could be of different size. So n could be 10, could be 100, 1 million, 1 billion, and so on. So to be able to compare training error on different training data sets, we need to normalize our error, because depending on how many samples, training samples we had, this sum will vary. So if n is 10, it might be, the error might be, I don't know, 1. But if n is 100, then the error could be 10, right? So if it's linear scale, so it could be 10. So we need to divide by the number of samples to make sure that we could compare our model trained on different size of training sets. Okay, so what else do we have here? Well, we take the root. The reason why we take the root is to get rid of this square. So when we sum up squares, we can take the root of this error function. So the units that we use to measure the error will be the same as the units that we use to measure y. So let me give you an example what I mean by that. Let's say we have, let's say this is temperature. Okay, this is temperature. So y is measured in degrees Celsius. So if we calculated the difference here, the difference will be given in degrees, right? So this is still degrees, but because we have square, that degrees will be squared, right? So to get rid of the square and get back to the original units, which are degrees Celsius, we take the root. Next is to start training process. After finishing training, we get a certain number. Let's say we get a number for M0, So that's just a constant. So we're looking for a best constant that we can have to approximate our data. This is going to be training data set, and this is going to be testing data set. Then we increase m to 1, and we repeat this process. So the training data set is this, and the testing data set is the error on the testing data set is this. So you can see testing error is always greater than training data set, and it makes sense because in training we did not use any data from the testing data set. We only use training data set. So in fact, our model could in theory just memorize all the points, all the data points that we have in the training data set. So the error will be 0. And that's what happened here. You can see the error is 0 because the number of training samples that we had was 9, and the polynomial order is 9. So polynomial order, the polynomial of order 9 could simply go through every single training sample. So the error will be 0. But the testing error is large. Okay? The reason why is because of those oscillations that we've seen in the previous slide. So the answer to our question, what is the best m for our problem, lies somewhere here. So one of these points will be the best one. So let's see which one is the best. Well, if we would only consider training data set, this would be the best case. But now we have the testing data set, and we can see that for testing data set, it's not the best. So because in machine learning, the main goal is to generalize and to make sure that our model will behave well and do well on unseen data, which is represented by the testing data set, we look at the error on the testing data set, and we want to have the minimum among this.